Hello! Welcome to today's lesson on how naturally occurring elements are produced from nuclear fusion reactions in stars. Today we will explain how nuclear fusion in stars creates elements, beginning with hydrogen fusion to form helium, and continuing through the creation of heavier elements like carbon and oxygen. Then we will describe how larger stars fuse heavier elements beyond carbon and oxygen, and how supernova explosions lead to the formation of elements heavier than iron. Finally, we will understand how supernovae disperse newly formed elements into space, contributing to the creation of new stars, planetary systems, and life. So far, you are familiar with the life stages of a star, from its formation to its eventual fate, whether it becomes a white dwarf, neutron star, or black hole. You understand the processes governing a star's life cycle, including nuclear fusion that powers stars and leads to their evolution. Building on this foundation, today's lesson will advance our understanding of physics by explaining the processes in stars that create all naturally occurring elements. This concept is crucial as it explains the origin of the elements making up our world and emphasizes the interconnectedness of cosmic events and the matter around us. Let's get started. You might have heard the saying that we are made of stardust, and that is in fact true. In this lesson, we will examine how processes in stars lead to the creation of elements. Stars begin their life cycle by fusing hydrogen atoms, which are the simplest and most abundant elements in the universe. In a star's core, the temperatures and pressures are high enough to enable hydrogen nuclei, protons, to collide and fuse to form helium. This is the fundamental reaction that powers the star and creates the brilliance we see in the night sky. As a star exhausts its hydrogen fuel, the core contracts and heats up, allowing helium fusion to commence. Helium nuclei undergo fusion reactions that form heavier elements, mainly carbon and oxygen. The fusion of 3 helium nuclei, alpha particles, forms carbon, while further reactions can produce oxygen. This phase continues the stellar process of creating increasingly heavier elements within the star's core. Our Sun and other similar-sized stars lack the necessary mass and core temperatures to fuse elements heavier than carbon. Therefore, such stars can only produce elements up to oxygen in substantial quantities. However, stars larger than our Sun have even higher core temperatures and pressures as they evolve. When these stars deplete their helium fuel, they can fuse carbon and oxygen into even heavier elements. For instance, carbon fusion can produce neon and magnesium, while oxygen fusion forms silicon. In these massive stars, the fusion process continues step by step up the periodic table, creating successively heavier elements. In massive stars, fusion continues until iron is produced. Iron fusion does not release energy, so once a star's core is filled with iron, it can no longer support fusion reactions. This leads to a catastrophic collapse of the core, followed by an explosive supernova. The extreme temperatures and pressures during a supernova explosion enable the formation of elements heavier than iron, such as gold, platinum, and uranium. This is due to a process called rapid neutron capture, or R process, where neutrons bombard iron nuclei, creating heavier elements rapidly. The supernova explosion disperses these newly formed elements into space, enriching the surrounding interstellar medium with heavy elements. These elements mix with gas and dust to form new nebulae. Over time, these enriched nebulae can collapse under gravity to form new stars and planetary systems, embedding heavy elements within them. This means that our solar system, including Earth, contains elements that were once formed in previous generations of stars. The fact that our planets contain elements heavier than iron confirms that our world was once part of a star. The journey of element formation in stars reveals that every atom of carbon, oxygen, iron, and gold in our bodies was once part of a star. The processes in stars have created the building blocks of matter that make up our world. This cosmic connection emphasizes that the universe is a dynamic, ever-evolving system where stars play a critical role in producing and recycling the elements found on Earth and beyond. By understanding the fusion reactions in stars, we grasp not only the life cycle of stars, but also the origin of the elements that constitute our planet and ourselves. This profound realization binds us to the universe, illustrating that indeed we are made of stardust. In today's lesson, we delved into how naturally occurring elements are produced through nuclear fusion reactions in stars. We started by understanding hydrogen fusion in young stars, where hydrogen nuclei fuse to form helium, releasing energy. As stars deplete their hydrogen, they engage in helium fusion, creating heavier elements like carbon and oxygen. We examined how more massive stars can fuse even heavier elements such as neon, magnesium, and silicon, continuing up to iron. These stars eventually explode as supernovae, where extreme conditions create elements heavier than iron, such as gold and uranium. The dispersed elements from these explosions mix with interstellar gas and dust, forming new stars and planetary systems. This journey of element formation shows that all atoms in our bodies and the Earth originated in stars, reinforcing the idea that we are indeed made of stardust. Understanding these processes not only illuminates the life cycle of stars, but also the cosmic origin of the elements around us. Watch the rest of the GCSE physics course at Sophos Education.